Good morning, everyone. It would have been a real pleasure to meet you physically and to exchange with the CSD&M community. It was not possible this year. My name is Jean-Rémy. I am the Representative Director of Digital Product Simulation KK DPS. For more than 10 years, DPS has been working on topics related to collaborative engineering. We believe that the methods and software we develop are an answer to the problems generated by the ever-increasing complexity of industrial systems. During this contributed talk, I will present a use case from the aerospace industry and illustrate the innovative answers that our new software Karen brings to these problems. So, these are the main topics I will cover. I will begin with a very macroscopic view of the challenge that our work addresses. Since there are multiple answers to this challenge, I will then elaborate on the use case seen we have been addressing, a more electric aircraft approach. The challenge is huge. Companies need to change, so I will focus on some of the problems they are facing and for which our method and our software provide solutions. Finally, I will discuss the simplified explanations of the use case we are dealing with. It will then be time to conclude before moving on to the question and answer session. Let's start by stating the problem. The world has changed, not only because of the new coronavirus. New players, especially Chinese, are seriously competing with the established airlines and aircraft manufacturers. The aerospace industry can no longer ignore the upcoming limitations in terms of oil resources. Thus, the entire aviation industry is striving to optimize aircraft performance and fleet availability and to reduce operating and maintenance costs as well as CO2 emissions. This represents a major challenge for aircraft manufacturers, their subcontractors and airlines. Multiple responses are needed, and therein lies the real complexity. Working methods must change. Competition between all players means that new designs must converge quicker thanks to frequent and short cycles. Development must be reactive and agile, just like the whole organization. Aircraft manufacturers therefore need breakthrough innovations. Given the scale of the projects and the heterogeneity of the technologies to be implemented, a single team, even a multidisciplinary one, cannot deal with the entire problem. The sharing of knowledge and information, but above all, the collaboration of the actors, will be a factor of success or failure. The aviation industry has embarked on an intense and irreversible revolution in onboard power systems, which are all gradually being replaced by electricity. At the aircraft level, rationalization of energy sources and networks, replacement of current circuits, mechanical, hydraulic, pneumatic, by electrical circuits controlling all aircraft functions. The result will be a significant reduction in the aircraft weight with a positive effect on CO2 emissions, the aircraft operational capacity, and therefore its fuel consumption and operating costs. The move towards a more electric aircraft represents a major technical breakthrough. This is generated by the mechatronics approach, which is by nature multidisciplinary. The design of these new systems, their integration into the overall system, is an iterative process that consists of a series of compromises. It is for this reason that we are interested in the case of the design and integration of an electromechanical actuator. It is a component which from the beginning must be thought in all its dimensions and which depends on a multitude of surrounding systems. It requires a technical mastery and a close collaboration between several disciplines. First challenge to overcome: working in silos. It has been said that the hallmark of all successful organizations is effective communication and a collaborative atmosphere. It has also been said that silos are not conducive to this communication, that they are a source of non-productivity, that they slow down processes, etc. This is certainly true. This is a paradox. Silos have developed quite naturally over time based on a logic of grouping specific skills to promote efficiency. Whether you like it or not, silos have proven their effectiveness. They are not the real problem. It is illusory, even counterproductive, to claim to break them. On the contrary, we want to organize collaboration from a different angle, by bridging different technical domains, by connecting their business applications to our current software. Our solution does not break down silos. It connects them and provides the necessary communication and collaboration flow. With Karen, a collaborative and connected engineering takes place and gives project managers and architects the possibility to step back from silos by detecting much earlier errors, technical conflicts, and inconsistencies between them. Traditional sequential engineering is a linear product development process. The steps follow one another and focus on one area of expertise at a time. The role of each person is well defined, and the level of progress of the project is easier to follow. The risk of a sequential approach lies in the non-existence of the information necessary for the development of the product at any given moment. As such, this approach is cruelly lacking in agility. Development times and costs increase due to the change requests in the final stages. This is not compatible with the development of a complex system. Our method greatly favors the adoption of a concurrent engineering approach. Karen synchronizes the development processes of each team on shared technical objectives and verifies the convergence towards a common solution as well as the achievement of the product performance objectives. Design changes are communicated to all relevant departments in a timely manner. The developments, the studies of alternative configuration, but also the evaluations of what-if scenarios are done in a concurrent way. Data useful for product development is scattered in many systems: PLM, Excel, reports, CAE model, etc. The amount of time wasted searching for the right, up-to-date information is abysmal. We choose to manage with Karen only the information necessary for the collaboration. This is an efficient approach to get around the reluctance of some people to share their model, their files, or when confidentiality issues between customers and suppliers come into play. This information is made up of data common to the whole project, high-level requirements, input-output between two distinct components, etc. The main principles that we implement with Karen are: we manage data at the parameter level. We do not manage models or files. Karen is the central piece that connects, without replacing, all the business applications used in the product development cycle, CATIA, Daimola, Windshield, ANSYS, Excel, etc., and manages their information flow. Information sharing is incremental. As soon as the new information is available, it is integrated and shared. Let's move on to our use case. You already know all this. The turns of an airplane are made with the help of ailerons controlled by the pilot and raised or lowered by an actuator. The aim of our work is to propose a preliminary study of this actuator with a more electric approach, and thus to replace a mechanical system by a mechatronics system. From a technical point of view, it is to explore different alternatives and 3 different possible architectures for the actuator. But the objective of DPS is to define, test the agility and validate some concepts of our collaborative development methodology on a concrete case, notably by implementing parallel studies and what-if scenarios. We want to verify the ability of the tool to provide all team members not only with the technical information they need, but also with the information concerning the progress of the project and its convergence towards an optimal solution. For this purpose, multidisciplinary resources were involved in this complex project: specialists in system engineering, CAD, simulation, cost analysis, security, etc. Karen is a web application designed to manage the complexity of a company's projects and their knowledge. Here you have a view of the user interface where several projects are managed. The knowledge structuring is organized in three main elements. 1. The product vision, which consists of the requirements and business rules of the company, expressed in the form of mathematical formulas. They define the relationships between the parameters but also the objectives to be reached. Second, the product knowledge, which gathers the key characteristics, the necessary and sufficient parameters for the collaboration, those whose value has an impact on several activities. 3. The points of view are there to reconcile the divergent technical interests defended by the teams. Take the example of the EMA gearing reduction ratio. It should be small for the mechanical strength and high for the point of view of the transition time between aileron up and aileron down. An informed decision will be made to set a common value for these common parameters. Finally, the consistency between requirements, viewpoints, and collaboration parameters is achieved by a mapping that links them. Let's see now how we implemented the case. First, we have connected to the Karen database the CATIA and Daimola software used by the system modeling and 3D modeling experts teams. Let's see how the project progresses. Karen is connected to the product requirements management application. The design parameters are constrained by one or more of these requirements: the power consumption, the response time, and here the mass of the system, which must be less than 5 kilograms. The information is retrieved and Karen then indicates the state of the requirements at that moment. The system is not reactive enough, the response time is too long. Let's see the convergence table. It lists the parameters common to several disciplines and their values when they exist. The design team is currently forecasting a motor power of 180 watts, while the modeling team is looking at a value of 200 watts. Karen identifies the incompatibilities between the proposals of the different actors common in the early phases. The project leaders are informed and engage in discussions to find a compromise. In our example, the common value of 180 watts is finally retained. The system modeling team will have to explore the options necessary to achieve this value. The simulation team advocates for a very compact motor to optimize performance. On the other hand, the implementation of such a solution poses real difficulties for the 3D modeling team because of interference issues with other equipment. But the solution they propose is not satisfactory. Discussions between the parties lead to a compromise. The engine footprint must be reviewed on both sides. An intermediate value is set as a common goal. As they progress, the designers send their value proposition to the other teams via Karen. This allows the project manager to monitor convergence. Compliance and convergence charts are complementary. During a complex project, the resolution of a problem sometimes leads to consequences elsewhere. In our example, it is on the simulation side, in terms of mechanical strength, that there is now an issue. Nothing is ever simple. So over time, convergence and compliance evolve. The dashboard of Karen provides an essential steering tool for all actors and provides the key information necessary for informed decision-making. Let's go back to the problems we identified and wanted to solve. Silos do not collaborate easily. They are the result of a logic of grouping skills that promotes efficiency. In this project, rather than breaking the silos, we decided to bridge them together and allow the exchange of data essential to collaboration by connecting business applications to Karen. Sequential work does not allow to explore the whole design space. Time is lost waiting for the necessary data. On the contrary, Karen favors concurrent engineering. With short cycles and few iterations, we studied 3 architectures of an electromechanical actuator and several of its variants. Deadlocked configurations are detected very early and eliminated thanks to compliance and convergence indicators. It is then easier to compare the designs and to discern on tangible criteria those with the best performance trade-off. Data is everywhere. It is in CAD models, in simulation results, in the Excel spreadsheet on your desktop, on post-it notes. Karen is a missing piece to manage technical data at the parameter level and the exchanges necessary for collaboration. It connects to existing systems and enables incremental information sharing between teams. Time wasted searching for information or reprocessing it is greatly reduced. My final word: there is no perfect design. All are the sum of trade-offs between the requirements of different domains. The innovation process is a strategy of trial and error. It is important to want to increase the number of trials and to detect errors as early as possible. Karen goes in this direction and helps designers, managers, and architects to make difficult decisions with full knowledge of the facts. Thank you for your attention.